let's look at how energy is actually exchanged between two systems now, again thinking about what's happening at a microscopic scale. Now, this is going to get into a lot of subscripts, so we're no longer using the TH subscripts to denote that this is thermal energy, but you should know that that's what we're talking about. One denotes what system we're talking about, because we have two. We're going to have an initial and a final to worry about. Now, one thing to note is that in this case, we're saying that we have two systems in contact through a very thin barrier. This is an ideal barrier. We assume that it does not move, that it doesn't conduct heat anywhere else, but it really simply prevents the two systems from directly mixing. We are then assuming that these two systems are completely insulated from the external environment. So we're also assuming in this specific case that they're both monatomic gases. Why? Why does that matter? Well, again, note if the relationship between energy and temperature is 3 halves, NkBT, from the equipartition theorem, we know that this must have 3 degrees of freedom. So this is only true right now for two monatomic gases. However, you could rederive this, you could follow through this argument with them both being diatomic gases, or in fact one monatomic gas and one diatomic gas. But right now, we're only talking about monatomic. So again, initially we can phrase this either in terms of our Boltzmann constant and the number of atoms, or the number of moles and the gas constant. So once we know that they're in contact but isolated from the environment, we know that our total energy is conserved, that we can transfer energy from one system to the other, but energy can't actually appear or disappear. So the sum of our two initial energies must equal the sum of our two final energies. So what's happening if we zoom in and think about individual molecules? Well, if we imagine two molecules colliding at the barrier, and again, this barrier is very ideal, we can pretend it doesn't actually exist. This is an elastic collision. Now, in elastic collision, energy is conserved, but that's total kinetic energy. If you go back and you look in detail at the kinetic energy equations, that you actually do have an energy transfer from one object to the other, right? Imagine an extreme case where you have one ball sitting still and another ball hits it. Well, you know that the ball that was initially still starts moving. Now, if the balls have different masses, they both end up moving in the end. And so your ball that was initially moving has lost some energy, and the ball that was initially at rest has gained some energy. So whenever you have a higher energy object and a lower energy object that are colliding, in fact, your higher energy object loses some energy in the elastic collision. The lower energy object, your slow object, gains some energy in the collision. But again, total energy is conserved here, so we've simply transferred energy. So in this situation, our faster atoms are the hotter ones. Our slower atoms are the colder ones, and we are transferring energy simply due to the nature of elastic collisions from our hotter, higher energy atoms to our colder, lower energy atoms. So what does this mean? This is really interesting. That initially we have two gases that are not in equilibrium. Let's say that temperature 1 is higher. Now we know that we have a temperature, we have that average kinetic energy of the individual molecules, and then we have our system thermal energy. And we know that all of these are related. These are kind of three different ways of talking about the exact same thing. But we see that if we zoom in and think about these collisions, we are transferring energy from the higher energy one to the lower energy one. Eventually, it reaches thermal equilibrium. What this means now is that these energies are actually the same. And this is where we have to be a little bit careful and think about what our equations are, which we'll go back to on the next slide. We said that these are three different ways of talking about the same thing, but there are some variables that are a little bit different, right? In this case, the picture shows that system 1 is smaller than system 2. So we would say that the kinetic energies, the microscopic kinetic energies, are the same. And the relationship between microscopic kinetic energies and temperature does not depend on how much gas there is. It doesn't depend on the number of moles or the number of atoms. So we see that we can directly relate temperature and microscopic kinetic energy. Thinking about energy transfer is really thinking about the microscopic kinetic energy. So because these two must be the same in order for these to be in thermal equilibrium, at this point there's no net energy transfer, that whenever they collide they just bounce off going out and you don't actually have a net transfer of energy in either direction. That means that these two temperatures are the same from this logic here. But thermal energy depended on how much gas there actually is. So these two thermal energies are not actually equal. So we're going to dwell on this a little bit. We see that our kinetic microscopic energies are equal. Our temperatures are equal, since these are directly proportional. But then what's not equal are our thermal energies, and that's because it actually relates to the amount of gas, in this case the number of atoms. But what you can actually say is that the relationship between the energy and the number of atoms divided out this way, these are equal. And when they relate at equilibrium, right, so this isn't true in general, but this is at equilibrium, that you can basically say that this is the total energy divided by the total amount of gas. So this is kind of a weighted average, that they reach this middle ground that does depend on how many gas atoms are there at equilibrium. Now the other thing that's worth noting is what heat then is. Heat is simply this microscopic energy transfer that you do not see if you're thinking macroscopically. But if we zoom in microscopically, we see that the energy transfer is coming from gas molecule collisions. But macroscopically, you don't see anything. You just see that one cools and one gets warmer. So then we know that the heat gained from one is the heat lost from the other, right? So because you must have no net heat, since these were isolated from the outside environment. And so then we can say, relate the changes in energies. So the change in thermal energy, since that's related to heat, will be equal in magnitude but opposite in sign. So it's important to distinguish between these three things. That at equilibrium, temperature and microscopic kinetic energy are absolutely equal. Thermal energy is not equal if you don't divide out how many gas molecules there are. Heat is going to be equal in magnitude but opposite in sign, which means that your energy change is also equal in magnitude but opposite in sign. You actually have to use some of these pieces of information for doing calculations, but it will depend on exactly what you're trying to calculate in your system.